Okay, we are going to kind of go back in time, as it were. As I mentioned in the last video, we're going to return to limits. Yeah, everyone's favorite. Except I'm going to make it a little bit different this time, and kind of like this, I think. I hope. We're going to return to indeterminate forms, limits that are indeterminate, and something called LHospitals rule. Sometimes this is written this way. I've seen it written other ways, I guess, and some people say it's the LHospitals rule, but I think the S is silent. So LHospitals rule is what we're going to encounter here, and so we are coming back to limits, and we'll be talking about why. Basically, limits again help us to understand the behavior of the graph of the function near certain portions of the graph. And we've encountered indeterminate forms before, so here's an example. If I plug in x equal 2 directly to see if I can evaluate this limit, of course there's a problem, denominator is 0, but so is the numerator, right? So that indeterminate form we talked about, 0 over 0, right? That means we had some work to do, and so remember how we did that. We basically said, hey, if I plug in x equal 2 and I'm getting 0 over 0, that means that x minus 2 is a factor of the numerator, right? In fact, we can factor this numerator as x plus 2 times x minus 2, and then we said, what? Hey, there's that common factor. I can simplify this. Since we're taking the limit as x approaches 2, we're guaranteed never to be equal to 2, and so we can say that the limit we're looking for is the same as this limit. And hey, this is easy, right? This function is continuous at x equal 2 and the limit is 4. And so basically what we're saying is the graph of this function here, x squared minus 4 divided by x minus 2, is exactly the same as the graph of x plus 2 for all values of x except for 2, right? And right at 2, of course, the graph of this function has a hole, and this graph here basically, which is a just a linear function, fills in that hole, so to speak. Okay, so the graph of this function is actually a linear function with a hole in it. But this is the way we evaluated these limits, if you remember. But what do we do in a case like this? If I plug in x equal 1, I get 0 in the denominator, and the natural log of 1 is 0 as well. That's indeterminate. That's 0 over 0. And there's no algebraic technique like we used in Chapter 2. And so what I want to introduce to you is a rule. The French mathematician L'Hopital gets his name on this rule. I don't know all the details about how this came about. I'm not going to prove this rule. From what I've read or heard, L'Hopital was a rather wealthy man and kind of liked mathematics, dabbled in it, and either stumbled upon this or maybe he bought it from somebody else, I don't know. But at any rate, we're going to use it free of charge. So suppose f and g are differentiable functions, and in particular g prime of x is not equal to 0 on some open interval about a. And suppose further that the limits of both of these functions as we approach a are 0, or that they're both infinite, plus or minus infinity. Then the limit as x approaches a of the ratio of these two functions, which based on these two conditions is either going to be what? 0 over 0 or infinity over infinity, plus or minus. And those are indeterminate forms. But L'Hopital's rule, here's where it kicks in, says this limit of the ratio of these two functions is equal to the limit of the ratio of their corresponding derivatives, provided this limit here does exist or is infinite. Okay? Now, so in essence, this rule, L'Hopital's rule, says that the limit of a quotient of functions is the limit of the respective derivatives. Again, provided there are several conditions here that have to be satisfied, and not the least of which is this limit on the right must exist. Now, keep in mind we're taking a derivative here. This is not the quotient rule. I'm not taking the derivative of this entire function here. I'm taking the derivative of the top over the derivative of the bottom. Okay, so it's not the quotient rule. And further, L'Hopital's rule does apply to one-sided limits as well as limits at infinity. So we can use it in all those settings as well. Somebody might say, well, why didn't you tell us about this rule before when we were doing limits? Well, hopefully you know why, and the reason being is we had to understand what derivatives in order to find, be able to use this rule. And so now that we know all about finding derivatives, we can now make use of L'Hopital's rule. So let's look back at a couple of these. We'll get to this one in just a minute. Let's actually look at this one using L'Hopital's rule. So we already know the answer, right? But let's see what it would look like using L'Hopital's rule. So L'Hopital's rule, again, we plug in and we get 0 over 0. That's indeterminate. So it's in the form that we can use L'Hopital's rule. Now when I use L'Hopital's rule, I'm going to indicate that with a big capital L. I like to put a circle around it just to emphasize. That indicates that I'm using L'Hopital's rule in this step. And so when I look at L'Hopital's rule, please remember it's the limit, right? So I must include the limit as x approaches 2. It's incorrect without the limit. And I take the derivative of the top. Well, that's not very difficult. What's the derivative of x squared minus 4? That's 2x. What's the derivative of the bottom function, x minus 2, with respect to x? Is just 1. And now this limit here is not indeterminate. If I plug in x equal 2, I just get 2 times 2 divided by 1, which is 4. And there's my result. Right? There's my result. And that's exactly what we had, of course, doing it the old-fashioned way. Right? But now, you know, like we said, what do we do with something like this? Right? We can now use L'Hopital's rule to evaluate the limit down here, right? If I plug in x equal 1, the bottom is 0, and the top, since the natural log of 1 is 0, we get indeterminate form again. But now I can't use those algebraic techniques, but I can use L'Hopital's rule. What's the derivative of the top function? Right? And the derivative of the bottom function is just 1. So if I plug in x equal 1, I get 1 divided by 1 over 1, which is 1 divided by 1, which is 1. A bunch of 1s. Right? So this limit is 1. Now, don't forget, we also talked about evaluating and estimating limits numerically. So don't forget that we have that to check even this process. So if I wanted to, I can come in here and input the natural log of x divided by, lighten the screen up just a tad. Divided by the quantity x minus 1. And go to my table, delete these values out, and let's get close to 1, right? From below, that's like 0.8, 0.9, 0.99, 0.999, right? What does it look like we're getting closer and closer to as we approach 1 from below? Looks like we're approaching 1. How about from above? What if we approach 1 from above, like 1.2, 1.1, oops, 1.1, 1.01, 1.001, right? Again, I'm getting closer and closer to possibly 1, it looks like. So we get support by checking numerically. So don't forget you have that tool. And as you're doing L'Hopital's rule, they may be a little more complicated in the process, right, with the derivative that we're taking and so on. But you can always come back and check numerically. Here's another problem that we actually found the limit of this expression with a geometric proof using the squeeze theorem. And that was a full page proof, basically. When I plug in directly, of course, since the sign of 0 is 0, I get an indeterminate form. With L'Hopital's rule then, since it's in the form 0 over 0, I can use L'Hopital's rule. Then the derivative of the top, what's the derivative of sine of x? Just cosine of x. Derivative of x is 1, and I can plug in directly cosine of 0 is 1. And we proved this limit was 1, but like I said, it was a full page. Squeeze theorem with all this geometric relationships, very elaborate proof we had to go through in some ways, and L'Hopital's rule, less than a line. So very powerful rule in a lot of ways. Okay. Let's look at some more. So these were fairly easy to do now with this rule, and then these were before either impossible or very difficult to do without. Plug in x equal 2. Up top I get 0. What's the sine of what? Pi times 2 is 2 pi. What's the sine of 2 pi? Sine of 2 pi. 0, right? So that's indeterminate form. We can use L'Hopital's rule. What's the derivative of the top? Negative 2x. What's the derivative of the bottom? What rule do I have to use to take the derivative of sine of pi x? What rule is it? Chain rule. Right. So the derivative of the outer function, the derivative of sine, is cosine evaluated at the inner times the derivative of the inner function. What's the derivative of pi x with respect to x? It's pi. But now notice I can plug in directly. Oops. I'll plug in. I can plug in directly. Replace x with 2. Pi times 2, or 2 pi. And what is cosine of 2 pi? It's 1. And so up top I get negative 4. And in the bottom I get pi. So this is negative 4 divided by pi. So that's a pretty cool thing, because that's a pretty difficult limit without L'Hopital's rule involving algebraic and trigonometric functions. But L'Hopital's rule makes quick work of it, so to speak. Okay. Here's another one that would be very difficult to do using algebraically, trying to prove this limit. Again, we could check numerically. But let's see what happens. First of all, when I plug in x equals 0, I get e to the 0, which is 1, minus 0 minus 1, so the top is 0. The bottom, cosine of 0 is 1, 1 minus 1, 0. Indeterminate again. So it's a candidate for L'Hopital's rule. So what do we have here? This is, again, don't forget, the limit as x approaches 0. What's the derivative of the top? Derivative of e to the x is e to the x. Derivative of x is 1. Derivative of 1 is 0. There's the derivative of the top. Derivative of the bottom, derivative of cosine of x is negative sine of x. Derivative of 1 is 0. Okay. So now let's plug in. Ooh, but wait a minute. When I plug in, e to the 0 is 1. 1 minus 1 is 0. Sine of 0 is 0. Oh no. This is still indeterminate. Darn. So it looks like L'Hopital's rule is not helping. Or is it? Well, what can we do here? This is indeterminate now, this limit, right? Could we use L'Hopital's rule again? Sure. Hopefully maybe we'll get somewhere. This has an indeterminate form 0 over 0, so I can use it a second time, right? So this is L'Hopital a second time. And so again, I still have the limit. I take the derivative of the top now. Derivative of e to the x minus 1 is just e to the x. And the derivative of negative sine of x is negative cosine of x. plugging in now e to the 0 over negative cosine of 0. E to the 0 is 1. Cosine of 0 is 1, so I have negative 1. 1 divided by negative 1 is negative 1. So I have the value of the limit. So yeah, you could sometimes use L'Hopital's rule more than once, like twice here. You might have to use it 3 times. Now, hopefully you're going to get somewhere if you keep getting indeterminate forms using L'Hopital's rule over and over and over again. That may not be very helpful. It is important, though, that we do get to a limit that exists. If you get to a limit that does not exist, then that doesn't necessarily mean the original limit does not exist. Okay, so we're getting the feel for L'Hopital's rule. Well, let's speed it up a little bit. Let's do some more interesting ones. Let's just, it says be careful. Well, we're careful. Let's just do it, right? Let's use it away, right? L'Hopital's rule. Limit as x approaches 1. Derivative of the top, that's easy, 2x. Derivative of the bottom is just 2. I can plug in 1. I get 2 times 1 over 2. Well, that's just going to be 1. All right. I got this stuff down. Turn in my test, Mr. Jackson. How did I do? Huh? What? It's all wrong. Right? Somebody watching this, I hope, knows why it's all wrong. Why is it all wrong? Because this is not L'Hopital rule form. Plug in x equal 1. What do you get if you plug in x equal 1? 1 squared plus 1 over 2 times 1 plus 1. I get 2/3. It's not 0 over 0. Limit is 2/3. This function is continuous at 1. And therefore the limit is equal to the value of the function at 1. Right? It's not 1, it's 2/3. So be careful. You do need to be in an indeterminate form, 0 over 0 or infinity over infinity. Look at one more example, but this time my example is going to be a limit at infinity. And there's several examples of taking limits at infinity. And so just reminding you, we want to be able to determine the behavior of particular functions at infinity. You should be familiar with the end behavior of x squared, and what's happening as x goes to infinity or minus infinity. X cubed, 1 over x, e to the x, e to the negative x. Graph of y equals natural log of x, sine of x. Inverse tangent x is interesting. Hopefully you realize where this comes from, right? It comes from starting with the tangent function and creating its inverse. And because the tangent function, its periodic nature, to make it 1-to-1, we restrict it on the interval from negative pi over 2 to pi over 2. And those, if you remember, become vertical asymptotes for the tangent function. Well, the inverse function is, for tangent graphically, is a reflection about the line y equals x. So those vertical asymptotes become horizontal asymptotes. And where do they occur at? They occur at y equal pi halves and y equal negative pi halves. Okay? So you should know those basic shapes. So, from these graphs, what's the limit as x goes to infinity for x squared? Going to infinity. What's the limit as x goes to negative infinity? Going to positive infinity. Right? What about x cubed? Going to positive infinity, going to infinity, going to negative infinity, going to negative infinity. The end behavior, if you will, for these functions. What about the graph of 1 over x as we go to infinity? What's happening as we go to infinity this way? The value of the function is getting closer and closer to 0, right? You can see that because the form of the limit is really 1 over infinity, quote unquote, right? 1 divided by a value getting bigger and bigger is going to go to 0. What happens as we approach x, as we approach 0 rather, from the positive side? So not going to infinity, but approaching 0 from the positive side. Well, we have a vertical asymptote here. As we approach 0 from the positive side, we're shooting up to positive infinity. And that makes sense again because I have 1 divided by 0 form, meaning I'm taking 1 and dividing it by a smaller quantity that's always small but positive. So that's going to go to positive infinity. E to the x, what's the limit as we go to plus or minus infinity of e to the x? Over here, right? Goes to infinity. As x goes to infinity, as x goes to minus infinity, what do we have? We have a horizontal asymptote of y equals 0. We're approaching 0, getting closer and closer to 0. So this is infinity, and this is going to 0. What about the limit as x goes to infinity of e to the negative x, which, by the way, you can think of as 1 over e to the x, right? Got the graph right here, but what's happening, we clearly see we're going to 0. And you can see it from this ratio, right? Since e to the x goes to infinity, 1 over e to the x is going to go to 0 as x goes to infinity. Okay, what about this then? Well, as we go to minus infinity, we see the e to the x in there, right? As x goes to minus infinity, e to the x goes to 0. So this whole term, what, is going to go to 0, and our limit will be 6/3, or 2. Natural log function, where is it going as x goes to infinity? Not as rapidly as e to the x goes to infinity, but it's going to infinity. It's increasing on its domain. What's the limit as we approach 0 from the positive side for the natural log function? So as we approach 0 from the positive side, vertical asymptote at x equals 0, right, we're going down to minus infinity. What's the limit as x goes to infinity of the sine function? I mean, I'll put it here, but you should know what it looks like. It's just going up and down. So what are we approaching as x gets larger and larger? Let's take it out a little further and let's see. Are we getting arbitrarily close to a particular value? No. We're just bouncing forever between -1 and 1. We'll never approach any one value. We'll never settle down to any one value. And therefore we say the limit does not exist. There is no limit. It's not infinity. It's not 1, not -1, not 0, but does not exist. And then we just looked at this one. What's the limit as x goes to infinity of the tangent inverse function? As we go to infinity, we have a horizontal asymptote of what, y equal pi over 2. We're approaching pi over 2. And for that matter, we can say the limit as x goes to minus infinity of tangent inverse of x is what? Negative pi over 2. Right, looking at it going this way, approaching negative pi over 2. So I expect you to be familiar with the end behaviors of all these graphs and be able to talk about limits at infinity. Just sort of a review. You'll need it as you go through the homework problems in the textbook, and so make sure you look at that. And by the way, you're going to be doing all the homework problems for these for this section in the textbook, and that information's in Brightspace. All right, limit as x goes to infinity. E to the x, we said, is going to infinity. X squared is going to infinity. This is infinity over infinity, and that's an indeterminate form. But it is also a L'Hopital rule form. And so I can make use of L'Hopital's rule. 0 over 0 or infinity over infinity. What's the derivative of the top? Well, that's e to the x. What's the derivative of the bottom? Well, that's 2x. Okay. Well, what's the form of this limit? Again, the top is going to infinity, the bottom is going to infinity. That's L'Hopital's rule again. Right? So we said last time we could do it again, right? Limit as x goes to infinity. Derivative of the top is e to the x. Derivative of 2x is 2. What's the form of this limit? Well, it's infinity over what? Well, as x goes to infinity, 2 stays constant. Is that indeterminate? No. Something going to infinity, something getting larger and larger divided by 2 is going to infinity. And so this limit is infinite. That means the original limit is infinite. how would this process change if this was x cubed here instead of x squared down here? And you can almost see what happens. Same forms, infinity over infinity for x cubed. The derivative of x cubed is 3x squared. And then we're right back to this one, right? Basically 1/3 times this limit, which this limit is infinity. We're still going to get to the same form, because every time I take a derivative of x, to any power, I'm just going down by one power, right? By the power rule, bring the exponent down, subtract 1, and so on. And so we, second degree, first degree, 0 degree. The numerator, meanwhile, is going to stay the same. Therefore, if n is greater than or equal to 1, the limit as x goes to infinity of x to the n, or e to the x divided by x to the n, is going to be infinite. Okay? And if you're a computer science person taking a look at limits of this form and comparing how two functions compare to one another as time progresses is important in analysis for efficiency and other issues. But just an example for you of a limit at infinity. Okay, in the next video we're going to take a look at some other indeterminate forms other than 0 over 0 or infinity over infinity, and we're going to use L'Hopital's rule to do those.